3 or 4 people, it looks like. Okay. All right. Today we're going to get into chapter 4 a lot more with derivatives, but let me just review the last few things of chapter 3 to know. One of which is the definition of uniform continuity. You should be able to state that on the second exam, what that definition is. Emphasizing, remember, like I said last time, it's always uniform continuity over an interval. You have to specify not just the function, but also what's the interval that you're talking about, because some functions, for example, quadratics, are uniformly continuous on some intervals, but not others. Quadratics, for example, will be uniformly continuous on any bounded interval, whether open or closed, but not on any unbounded interval. Whereas linear functions actually are uniformly continuous on any interval. Intuitively, the slope is constant, so that's why the same delta can work for any epsilon. But there is the Uniform Continuity Theorem. Should be able to state theorems for tests, right? Anything that's a named theorem is fair game for the test. The book does not give it a name, but I am. Okay, I'm calling it the Uniform Continuity Theorem. It is the main theorem about uniform continuity, Theorem 3.28 on page 112. If you've got a continuous function on a closed and bounded interval, it does need to be closed, right? Because we saw 1 over x was not uniformly continuous on the open interval from 0 to 1. It's got to be closed. Once you've got that closed interval, continuous function on that, you know it's going to be uniformly continuous. That's the most basic important fact about uniform continuity. And you should be able to state that for the next exam. We use it in chapter 5 to prove that continuous functions are integrable, Riemann integrable on closed intervals. They can be integrated, so to speak. And yeah, that'll be our main application. How many named theorems have we had so far in chapter 3? Well, there's intermediate value theorem, extreme value theorem, uniform continuity theorem. I guess the squeeze theorem is a named theorem. If I say the word linearity, well, like with limits, it means the limit of a sum is the sum of the limits, for example, as one aspect of linearity, or the limit of a linear combination of functions, more generally. I've got 2 functions here, but I could have n functions, is the corresponding linear combination of the limits when those limits exist. When you assume the limit of f and the limit of g exist as x approaches c, then the limit of this function, where a and b are constants, will exist and will equal that. That proof of that could show up on the exam, epsilon delta proof, for example. So that's a linearity property of limits in this case. Limits have other properties that you wouldn't typically be called linearity, like the limit of a product is the product of the limits. That does not carry over to derivatives, for example. The product rule is the way you differentiate derivatives, and that's not a linearity property, but that's an example of a linearity property, and that kind of thing holds for derivatives too. You should know those factual things that I mentioned. Monotone functions are nice. One-sided limits exist at every point. That doesn't happen with non-monotone functions in general. The set of discontinuities is countable. That doesn't happen with non-monotone functions in general. The main example we saw is the function that jumps up and down between 0 and 1. It's 0 at every rational and 1 at every irrational, or vice versa. They're mostly differentiable. They're differentiable almost everywhere. We're leaving that concept of almost everywhere undefined. That actually is a mathematical term that it has a good definition of what it means to be, for something to be true almost everywhere. Kind of a strange thing to have a mathematical definition, but it does. And we can integrate them. They are Riemann integrable. So we are focusing on the Riemann integral in here, not the Lebesgue integral. We're going to prove that you can integrate monotone functions. Are they really nice though? Actually, monotone functions can be somewhat strange. There's something called the devil's staircase that evidently Cantor thought of because it's also called Cantor's function. It's related to the Cantor set. Have I mentioned the Cantor set in here? Let me briefly mention what the Cantor set is about. If you let K1 be the closed interval from 0 to 1, let K2 be the interval obtained by taking out the middle, the open middle third of this interval. Consider the union of the closed intervals from 0 to 1/3 and from 2/3 to 1. We're going to call that K2. K3, the next step, I'm going to take out the open middle thirds of those intervals and get a union of 4 closed intervals whose endpoints would be 0 and 1/9, 2/9 and 3/9 or 1/3, 2/3, 7/9, 8/9 and 1. And you keep going. K4 would be the union of 8 open intervals. Take out the middle open middle third of these, so you get intervals from 1 to 1/27, from 2/27 to 1/9, from 2/9 to, what would it be, 7/27. Should be right about there, etc. You'd have 8 of them. And you keep going. The Cantor set is the intersection of all these sets here. It's a pretty strange set. It's an example of a fractal. It doesn't contain any intervals. It's something called totally disconnected, and its complement seems to maybe take up most of the interval. Like its complement includes that, it includes that, it includes that. It includes the interval from 1/27 to 2/27. Right in there. Its complement seems to sort of take up most of the interval, but the Cantor set is still actually uncountable, amazingly enough. And it's a fractal. And you zoom in on any part of the Cantor set, it's going to be what's called self-similar. It's going to look like another copy of itself. Okay. If you don't quite get this, it's hard to get. Okay. It's sort of a sometimes called Cantor dust. It seems like it's dust sort of scattered over the plane, but it's actually an uncountable set. Anyway, based on the Cantor set, you can make something that we call the devil's staircase. This is code by somebody named Douglas Rivers that I got off the Wolfram Demonstrations project. And what's going on here? We've got a function that we're going to define at a certain number of iterations. And we can also magnify it. We can zoom in. The first step in defining this function is to let it equal 1/2 between 1/3 and 2/3. So 1/3 is right about there, 2/3 is right about there. On that first middle third that we took out on K2, we're going to let this function we're defining to equal 1/2. At the next iteration, the next step, we define 2 new pieces of it. Here the output is 0.25, here the output is 0.75. This is defined on the open interval we took out between 1/9 and 2/9 for K3. This one is defined for the open interval between 7/9 and 8/9 that we took out. Keep going. Next iteration. is, okay, far lower left corner there. The output there is 0.125, I believe, halfway between 0 and 0.25. And that is defined to be what it is on the open interval between, I didn't draw it here, 1/27th and 2/27ths. The next one right in here, come back up to the screen, should be a 0.375. That is defined to be that way between, it would be 7/27ths and 8/27ths of the open interval that I take out for K4 that I didn't draw. Etc. You've got these other definitions up here as well. You keep iterating to define this function, and you get a staircase-looking thing that you can zoom in, and it's got a self-similarity kind of property. It looks similar to itself. The more you zoom in, it basically looks the same. Actually, it only looks technically the same when you let the number of iterations go to infinity. This function is constant on the complement of the Cantor set. Somehow it only increases on the Cantor set, even though the Cantor set is like dust. It's totally disconnected. It doesn't contain any intervals. Weird. It's pretty weird. It's monotone, so it's nice because it's monotone, but it's still strange. Somehow, even though this Cantor set, the intersection of all these sets, is totally disconnected, it contains no intervals, somehow this function is only increasing on the Cantor set. And it's constant on the complement of the Cantor set. Yet overall it increases from 0 to 1. I think that's pretty amazing. I think that's pretty strange. It gets stranger and stranger actually the more you think about it. Okay? I will try to give you hints about some possible foundations of math projects for your interim class in January. You know, you could study fractals for your foundations of math class for your the paper that you do in there. And the Cantor set and this Cantor staircase, the double staircase, could be considered as part of your paper. How much do you need to know about the variation of a function and functions of bounded variation? Well, you should know the definition. I realized after the end of class on Monday that I forgot to say what does it mean for a function to have bounded variation. I put it in as a little annotation in the video. We define the variation of the function over some interval from C to D to be a supremum of summations like this, where this set consists of all possible sums you can make like this over all possible partitions of the interval from C to D. Take the supremum of that. I said this could be an unbounded set, not bounded above, and so technically it's a sup in the extended sense that it could equal infinity, so to speak. However, if it is finite, if the supremum is a real number, then we say the function f has bounded variation on the interval from C to D. So you should know the definition of the variation. You should be able to describe what this set is supposed to represent. It's sort of bad notation for the set. The set of all possible values of summations like this over all possible partitions of the interval from C to D. So you kind of got to describe it with words. You should be able to do that, and you should be able to say, hey, if that supremum exists as a real number, not infinity, then we say the function has bounded variation. I think that's mostly what I'm going to want you to know for the test. I hope you did try your best to go through the proofs and try to understand them from that section. I know they were harder than typical. Because if you did, you're going to be rewarded when you get to Chapter 5 on integration, because the proofs have a similar feel. And in Chapter 5, your homework proofs are not going to be quite that difficult. Not as difficult as the proof, for example, Theorem 3.36, page 120 is kind of a long proof there. Kind of a difficult proof, but it gets you in the mode of thinking to help you in Chapter 5. So if you haven't forced yourself to struggle through these, I still think it's worthwhile. Try to get in that mode of thinking to help you for chapter 5. That's probably the main benefit of struggling with section 3.5 for us, with this idea of variation and bounded variation. All right, for the rest of the class, we're going to go on to derivatives. Let's start with the derivative calculation, and we'll talk about the theorems. So we did one calculation. Last time, the derivative of x squared, and we did it in 2 ways. Let's try derivative calculation for the function f of x equals 1 over x squared for x non-zero. And let's do that in 2 ways as well. Okay? First way, the way we typically teach in calculus is a limit that looks like this. I want to shut the door there in case some noise is coming through. Right, this is, if you TA in math lab, or just grade papers, this is the kind of limit you see a lot in Calculus 1. You should be able to do these calculations. It's always good to practice these a bit. For this function, it would look like that. And to simplify this, you can do 2 things which are really equivalent to each other. You could get a common denominator up top and subtract the fractions and then divide by h. Or, it's maybe a little quicker, is to multiply the top and the bottom by x squared times x plus h squared. So that you get rid of the denominators there. I'm showing the step, but really you could do it without actually showing that part. You could just say this limit equals the following limit. Looks like that. Right at the top we get cancellation after using the distributive property. X plus h squared cancels there, the x squared cancels there, leaving us with this. Nothing cancels on the bottom. What you're always hoping with these things is that you can divide out the h on the bottom so that you can plug in h equals 0. As for constant x as a function of h, this is undefined at h equals 0, but maybe the limit still exists as a function of h as h approaches 0. The x squareds will cancel on top. Got to bring the minus sign through the parentheses there. Factor out an h with what's left. And divide it out with the one on the bottom. Which is okay to do because, why? Because the limit of the function doesn't depend on what happens to the function at the point in the definition of a limit. This function, again, for fixed x, think of this as a function of h, is technically undefined at h equals 0. But if you graph it, the limit is going to exist. There'll just be a hole in the graph at h equals 0. So ultimately, the dividing h out will be justified by the fact that the resulting function will be continuous at h equals 0 and will have a limit. So I'm going to do 2 steps at once here. Bring the negative sign through, divide out the h's, and write it now like this. For a fixed non-zero x, you hear me? For a fixed non-zero x, this is continuous at h equals 0 as a function of h. Now we can plug in h equals 0 to evaluate the limit. And that will give us negative 2x over x squared times x squared. negative 2 over x cubed, negative 2x to the negative 3, if you prefer, which is the same thing that we get if we applied the familiar power rule to this thing. Let's do the calculation the other way and see that we get the same thing.
I got a question.
Mm-hmm.
Whenever, so this little trick you did here, how many different tricks are there? Because there was one that we did differently on last class to just know.
Just got to practice enough that you just sort of naturally know what to do.
That's why I'm asking how many different.
I don't know if I can quantify it. I mean, multiplying by 1 in a convenient way is a common trick, but with each problem it might look different.
Okay.
So I don't know that I can quantify exactly how many.
So those are two major ones, multiplying by.
Adding 0 in a convenient
denominator.
way and multiplying by 1 in a convenient way, yeah. And in this case, yes, so you can cancel the denominators at the top. With square roots, it's nice to be able to. We should do an example with square roots too. Here's the other way the book writes it. It's a little odd to use the letter V perhaps, but this is certainly okay. Let's see what happens with this one. Maybe I'll do this one by actually subtracting the fractions instead of multiplying the top by x squared times b squared and the bottom by x squared times b squared. Let's actually subtract the fractions. I'll bring the v minus x out front as a 1 over v minus x. Now get a common denominator of v squared times x squared. So all I did there was just subtract the fractions. I got the common denominator of v squared times x squared. Turns out you can factor the top. X minus v times x plus v. And that x minus v is going to divide out with the v minus x, except it won't leave you with a 1, it'll leave you with a negative 1. That's where the negative sign comes from. So we get negative x plus v over v squared x squared after cancellation. Now plug in v equals x. This is a continuous function. See, x is fixed here. This is a continuous function of v at v equals x. This wasn't. Because when v equals x, you'd be dividing by 0. When x is non-zero here, we're not dividing by 0. This is a continuous function of v when v equals x. I can now substitute v equals x in here. And once again, get the same thing. Let's do one with the square root. Just square root of x. Mm-hmm.
How do you get the negative from the part that's circled?
X minus v and v minus x divide out as a negative 1, since they're opposite order. Let's go back to the other limit for this one. Oh, maybe we should do it this way. I don't do it this way as much. So I'm having a little fun doing it this way. What do you do here? There's two things you could try. There's two ways to do this. You could try to factor the bottom as, well, you can factor it as square root of v minus square root of x times square root of v plus square root of x. It does factor like that. As long as v and x are positive. And then cancel there and there. Or a trick that works more generally, including with the other limit, is to multiply the top and the bottom by this. So once again, a trick here. This is a common trick to use with square roots. Multiply by that because when you FOIL it out on the top, the square roots are going to go away on top. It's not a guarantee that it's going to be helpful, but with these kinds of problems, it turns out it is helpful. You just get b minus x up top. And that'll now divide out with the b minus x in the bottom. And as long as x is non-zero, x has to be positive here. Then you can evaluate this limit. If x were 0 and you'd be letting b go to 0, that wouldn't be good. So if x is positive, then we can say this equals 1 over square root of x plus square root of x, 1 over 2 square root of x, or 1/2 x to the negative 1/2. Which is what you get when you apply the power rule to that. What about the derivative at 0? Does that exist? The derivative at 0, let's go back to the other limit, would look like this. Technically, we'd be letting h approach 0 from the right. And that limit does not exist. And therefore, this function is not differentiable at x equals 0. By the way, in the definition of differentiability with f prime, you can assume the point you're trying to differentiate is an endpoint of a closed interval, for example. If it is, you just take a one-sided limit. That's mentioned in the textbook. But even as a one-sided limit, we're not getting differentiability here at 0. The graph of the square root of x function looks about like this. Gets up to 2 when you're up to 4. This is a bad picture. Okay, pretend that's a good picture. And the slope of the tangent lines, the slopes of the tangent lines approaches infinity as you get closer and closer to the origin. If you consider there to be a one-sided tangent line at the origin, it would be a vertical one, which has undefined slope. You might say the slope's infinity, but for us, we'll say undefined. All you derivative rules you should, of course, know. And they're all great things because they help us avoid limit calculations. So just as a review, what if you wanted to differentiate? Oh, let's make it fairly complicated. X squared cosine of x cubed over e to the x squared. Amazingly, it can be done, right? These derivative rules that you just take for granted are really, really amazing. The fact that we can differentiate something like this at all is amazing.
And you're going to do that the long way?
Not with limits, no. I'm going to use derivative rules. I don't want to do it with limits, no. It's a quotient at the most basic level, the most fundamental level, you might say, so we've got to use the quotient rule. I learned the quotient rule as low-d high minus high-d low over the square of what's below. Anybody else learn it that way? Maybe if you took calc from me, you did. the bottom times the derivative of the top minus the top times the derivative of the bottom over the square of the bottom. That's kind of more long-winded to say. It's more fun to say low d high minus high d low over the square of what's below. But you got to start right. You got to start with the low. Low d high means the derivative of the high one. I'm going to write out all the gory details in terms of carefully writing these rules here. Low d high minus high d low over the square of what's below. You could also multiply those two exponents. Maybe in the next step I will. Then with this derivative, at the most fundamental level, this function is a product. I need the product rule. Here I can just get away with just the chain rule. No product rule there. But let's write out the details to be careful here. We've got the first function times the derivative of the second plus the second function times the derivative of the first. Of course, ideally you do this kind of stuff without writing all these ddx's. Chain rule. Differentiate e to the x squared. By the way, I hope it's clear to you that e to the x squared means this. It does not mean that. Because if you meant that, you'd write it like this. And those are definitely different things. So you do x squared first, then you exponentiate. So the chain rule says we've got an inside function x squared and an outside function e to the x. Differentiate the outside function, the derivative of e to the x is e to the x. Plug in the inside function into that derivative. Plug in x squared into e to the x. Get e to the x squared again. Times the derivative of the inside function. And I'll write the bottom like this. Technically, I need the quote of the chain rule here too. I'm not going to bother writing any more ddx's though. That'll be 2x. The final answer let's see. I guess I could have canceled one of the e to the x squareds, couldn't I? That and this cancel with one of those to leave an e to the x squared in the bottom. To make it a little simpler as well, so we get, still got to be careful here. I'm looking right here, use the chain rule. Derivative of cosine is negative sign. I'm going to get negative sine x cubed times 3x squared times x squared. So it'll be negative 3x to the fourth. Sine x cubed. From that one. Be thinking with me to make sure I don't make a mistake. Plus that will be 2x cosine x cubed minus, you get a 2x there, combined with the x squared there gives you minus 2x cubed cosine of x cubed, all divided by e to the x squared. There we go, if I've not made a mistake. This should be right. Well, by definition, if I haven't made a mistake, it should be right, right? That's amazing! We can differentiate this thing and get that, no limits. And the values of this function are going to give you the slopes of that one. You can use it to figure out critical points. I don't think I want to do it though. Well, one is at x equals 0. approximate them by finding the zeros of this approximate. Okay, derivative rules are amazing. You should be able to do your calculus 1 kinds of calculations like this. I might put a derivative on the test, okay? Just for the sake of making sure you get out of here a graduating senior and you do know how to differentiate something like this as a math major, okay? You should know the derivative rules in their abstract form though too. For example, the chain rule can be written as d dx of f of g of x, assuming f and g are differentiable on appropriate intervals. Right? Books got these things written as theorems, so we have to worry about saying what the intervals are to guarantee that this thing is going to be differentiable appropriately. In an equation, the heart of the chain rule is like this. G is the inside function, f is the outside function. Take the derivative of the outside, plug in the inside, multiply times the derivative of the inside. The abstract form of the chain rule, you should be able to use that. You should be able to write it down as an abstract formula. If I give you tables of values of f and g and f prime and g prime, you should be able to plug in numbers even if you don't have formulas to find a derivative of something like this. You know what I'm talking about? If I gave you a table of appropriate values of these things, I'm not going to bother coming up with an example. You should be able to find the derivative of this at some number x if I give you appropriate information, which would include knowing what f prime of g of x is, for example. You'd have to be able to tell that from the table. So if x was 1 and g of 1 was 2, you should be able to differentiate. You should have in the table f prime of 2, for example. Did you catch that? If g of 1 was 2, you better be able to find f prime of 2. Here's something kind of fun. You can use the chain rule and the product rule to derive the quotient rule, sometimes just as a derivation, not really a proof. I have people do that. You want to derive the quotient rule from the chain rule and the product rule. You can write the quotient as a product. That. This is not an inverse function, it's a reciprocal. So I'm putting the -1 outside the parentheses like that. Now I use the product rule, the derivative of the first times the second, assuming these derivatives exist and we're not dividing by 0, plus the first function times the derivative of the second, which I need the chain rule for, and the power rule, bring the -1 down in front. Subtract 1 from that exponent, multiply times the derivative of the inside function. Now simplify, get a common denominator of g of x squared. If you do so, notice the minus sign there, you're going to get the quotient rule. By combining these as fractions. Low d high minus high below over the square of what's below. Kind of a fun little derivation that I've sometimes put in tests. It's not, these things are not really real analysis kinds of things, but okay, because we're not worrying about, at least in my lecture here today, I'm not worrying about hypotheses, I'm not really doing proofs, I'm doing derivations, but I think it's worthwhile to go over these because every math major should know these derivations. Should make sense to you here, you should be able to do it for the test. Another kind of derivation. Derive, for example, the derivative of the arctangent function. Oops, arctangent, not arcsine. We know this equation is true for all x, actually. There's no restrictions on x here. This equation is true for all x. If I did sine of arcsine of x equaling x, that has restrictions on it. This equation is only true over the domain of the arcsine function, which is x between -1 and 1. Yeah. This is true for all x. X could be a billion here, and it still works. Again, this is not a proof. Assuming the derivative of the arctangent exists, assuming this is a differentiable function on the left and the derivative of the arctangent of x exists, we can use the chain rule to differentiate the left side to say, well, the derivative of tangent is secant squared. Plug in the inside function, then multiply times the derivative of the inside function. So you see I am implicitly assuming that derivative exists in writing this. This is a derivation, not a proof. Derivative of x is 1. Solve for the derivative you want to. Fine. The derivative of the arctangent of x is 1 over that, which is the same as cos squared arctan x. That is the answer. Was that what you would write in a Calc 1 gateway? No, it's not what you would write in a Calc 1 gateway because it's just not an usual form. It is the answer, actually, though. That is the derivative of the arctangent. But how do we usually write it? We usually write it as 1 over 1 plus x squared. And if we go ahead in our deriving mode and think about right triangles, label this angle arctangent of x. So katoa.
How do we skip straight to cosine squared arctan? Didn't we have 1 over arctan?
It's 1 over secant squared of arctangent of x.
With the 1 over
But the secant is 1 over cosine.
Because the secant's 1 over cosine, but the arctan, wouldn't that still be under the 1?
No, you're plugging it into the secant squared function. So it's still got to be input for the cosine squared function. So katoa, tangent is opposite over adjacent. The tangent of this angle is x. So I can take this side to be x and this side to be 1. Or 2x and 2, or 3x and 3. By the Pythagorean theorem, the hypotenuse has length square root of 1 plus x squared. Cosine, cosine is adjacent over hypotenuse, 1 over square root of 1 plus x squared, but we're squaring the cosine so the square root goes away. There we go. There's our derivation of the derivative of arctangent of x, and this works for all x. Again, it's a derivation, not a proof. These are just kind of fun too, to me, so it's like still worth putting in one real analysis lecture at least. I hope you find these kind of fun too, maybe compared to epsilon delta stuff. These are fun. Actually, you can generalize this derivation to this kind of equation. And here, that does mean inverse function of f. It does not mean f of x to the negative 1 power. Our book, tries to avoid that confusion by using f sub I and v for the inverse function, which is great. But you future teachers will be teaching this notation, so might as well. Again, assuming all appropriate derivatives exist, I differentiate both sides with respect to x. Oops, wrote this wrong, typo. I'm not having the ddx there yet. By the way, this would be true for all appropriate x in the domain of the inverse function. Whatever that domain might happen to be. Now use the chain rule. Assuming this derivative exists, solve for that derivative. The derivative of the inverse function at an arbitrary number x in its domain equals 1 over the derivative of the original function at f inverse of that arbitrary number, assuming we're not dividing by 0. Now this is pretty confusing for people. You got to be really careful when you use this. Let's consider a function whose the formula for the inverse function would be very difficult to find. Like x cubed plus x plus 3 or something. Technically speaking, you can find a formula for the inverse function, but it's pretty complicated. It's cubic here. I might want to find, let me think here. Find the derivative of f inverse. Oh, let's make it be at the input, thinking here, 13. Find f inverse prime of 13. The inverse function does exist. You graph this function, it looks like this. It's 1-to-1, passes the horizontal line test. It's got an inverse function. And the graph of the inverse function, you could graph as the reflection across the line y equals x. So the inverse function will look about like this. This is always a challenge. Something like that. Find f inverse prime of 13? What's with this 13? Anybody think they know why I put a 13 in there? It makes it easy to calculate, possible to calculate, by putting a 13 in there of all things. Whereas if I pick a 12, it wouldn't work so easily. What makes 13 work easily with this? It's not obvious to most people. This picture's not real great. F of 2 equals 13. 2 cubed is 8, plus 2 is 10, plus 3 is 13. F inverse of 13 equals 2. That's why we're going to be able to do it. According to this formula down here, this is 1 over f prime of f inverse of 13, 1 over f prime of 2. Now we just have to find f prime of 2. F of x, or f prime of x is 3x squared plus 1. So f prime of 2 is 13? Yeah, 2 squared. 13, that's just a coincidence. Okay, there we got a 13 again. This is 113. The slope of this graph at the point 2, 13, the slope happens to be 13 as well. not to scale here, okay, bad drawing. At the point 13.3 on the inverse function, 13.2, excuse me, the slope of its tangent line is the reciprocal of the slope of that one. The slope here is 13, the slope there is 1/13. Again, the 13 just happened to come up again. I didn't know that was going to happen. Differentiability implies continuity. The function's differentiable at a point, it's also continuous there. Therefore, by contrapositive, if it's not continuous at a point, it's not differentiable there. So if you've got a corner in your graph, excuse me, if you've got a break in your graph, if it's not continuous at a spot, it's not differentiable there. Differentiable means derivative exists. But not the other way around. Remember at the beginning of the semester we saw there was an example of a everywhere continuous, nowhere differentiable function. Its graph is really a fractal. Here we're getting better and better approximations to it as I iterate here. Okay? In the limit, the graph is a fractal. It's self-similar in the sense that if you zoom in near any point, it's still going to be jagged, about the same level of jaggedness, no matter how far you zoom in. So it's continuous everywhere, but differentiable nowhere. You also want to be careful for, well, I guess like with the square root of x functions, where the tangent line is vertical, even if they're defined everywhere. For example, the cuberoot function. Technically, that's defined everywhere. It's even continuous everywhere. Graph looks about like this. But at the origin, there's a vertical tangent line. If you zoom in near the origin, the graph looks more and more vertical. It does pass the vertical line test, by the way. No vertical line goes through it more than once, including the vertical line that's the y-axis here. It only goes through it once. But the tangent line is vertical. The graph looks more and more vertical as you zoom in near the origin, closer and closer. This function is not differentiable at 0, which you might say isn't surprising since when x is non-zero, the resulting function is not defined at 0. However, that's not a proof. To prove f prime of 0 does not exist, you need to do the limit calculation, kind of like we did with the cube root. Oh, sorry, the square root. About a half hour ago or whatever. Okay, so you do need to be careful. I guess today was a Calc 1 lecture in real analysis. Okay, essentially we did Calculus 1 stuff. You should study the book and understand the proofs. You should be able to prove the product rule, by the way, which is the trickiest proof the book does. Which does involve a trick, by the way, a trick of adding 0 in a convenient way. It's not a real long proof, but it's a little tricky. And definitely study section 4.2 real well before next Monday, because we're going to go deep into the theory again. 4.2. And a little bit of 4.3 might not be bad to get into as well. Just to preview a little bit. Nice long weekend here. See you next Monday.